Yo creo que sí. Hello? Okay. It works.
Ya lo puedo poner. No quieres hablar con todo el mundo.
Ya.
¿Estás preparada?
No, estas cosas me ponen súper nerviosa. O
¿Por
creo que ya
qué?
está grabando. ¿Mm?
Creo que lo puedes apagar también. Ya, lo puedes apagar arriba.
No, está bien, yo lo dejo así.
No, pero igual todavía no está en live stream, ya me imagino.
¿Cómo sabes? No, me dijo 5:55. O sea que...
Bueno, todo bien entonces. Sí, me acabo de tomar un café. Me lo presenté.
Eléctrica. Dale, gracias, chao. ¿Ah? Oh, I know. That's a good one. Let me see what time it is. I'm hoping. 2 hours. But I hadn't realized it was 22 pages. Sorry. Okay. Good job too. Hey, that's all. Let me see what time it's.
So, you know how you said that you use your, I don't know what's it called, ACS book, whatever, like to study? There's like a lot of practice problems. Like, how many do you do like per section?
Uh,
I'm just asking because like I only have one day. I don't always know.
just, you know how they have like questions inside of like the things they cover? Do those. If you have trouble, if you don't get those right, then focus more on those and yeah.
Okay, especially the ones that have like the explanation.
Yeah, because then that gives you like an idea of where are you having trouble and what should you do. That's what I did. Good luck. You got this.
Do you already take any finals?
Hmm?
Do you already take any finals?
I took 2 yesterday.
Oh my god.
Yeah, back to back, 10 minutes apart. It wasn't pretty. And I have another one on Thursday, so. I have another one on Thursday.
And then you're done?
Yeah.
I don't know why, like, all my friends are like at the end of the week and I'm just like, why? Oh, why?
You got this.
Yeah.
Let me see what time it is. I took 2 yesterday. I have 1 on Thursday. Molecular Biology 1, Microbial Metabolism, and Tissue Engineering. Yeah. Thank you. All right, sit. All right, hi guys. It's officially sits, so we can begin. So as you know, I always start with a bad chemistry joke, and I had to Google one because I didn't have one. So a photon checks into a hotel and he gets asked, "Do you need help?" And he's like, "No, I'm traveling light." So I know they're bad. You guys don't have to clap. Okay. All right. Let me know if at any point, like during the session, you guys need me to move up like the paper or anything. Just let me know. Yeah. There we go. All right. So, as a reminder, even though like this review touches on a lot of concepts, it's not like comprehensive. So make sure you're studying from the textbook and the slides. This is just like a complement to that. Keep that in mind. All right. So that's that. All right. So I think I cover it based on how we cover the class, like chapters 1 through 10 and then 5. So, and feel free to ask questions if you have them throughout the session. I'm going to try to keep like a study pace so that we can finish the whole packet, but if you have questions at any point, just ask. Yeah? Can you talk a little louder? Let me see if I can turn this up. I can't, so I'll try to speak louder. I guess not. Okay, well, is that okay? Better? Hello? Oh. Okay, I'll try to stay like this. All right. I don't know what that was. Okay, so matter is anything that has a mass and occupies space. And it's composed of atoms, submicroscopic particles, which are the smallest objects that are called matter. And molecules are two or more atoms held together by bonds. Then we have like some things in chapter 1 that are related to like hypothesis, experiment. So hypothesis is a tentative interpretation or explanation for an observation, and an experiment is a set of procedures designed to test a hypothesis. There's two types of observations, qualitative or quantitative. The qualitative describes how a process happens, and quantitative measures a process. A law is a summary of observations, cannot be violated, and allows you to predict future observations. A theory is an unifying principle that explains facts and laws. So a law would be like the law of conservation of mass. Whereas a theory would be like the atomic theory. All right. I try to do this review like concept question type of thing. That's how like it's set up. So for question, a chemist mixes sodium with water and witnesses a violent reaction between the metal and the water. This is best classified as observation. I'll go a little faster through like this like foundation stuff so that we can spend more time on like the harder material. All right, so classify each of the following as either liquid, gas, or solid. What should you add during each step in case to get to the net state of matter? What type of reaction would it be? So be sure you're able to identify graphs. So this is solid because they're all like clumped together, liquid, and gas. And so from solid to liquid to gas, you need to add energy. or heat. So this is an endothermic reaction. Let me turn the page. All right, fits volume and shape. It's a solid. Fits volume and indefinite shape, liquid, because it takes the shape of the container it's in. And indefinite volume and shape, it's a gas. All right, so we have matter, and we can classify it as a pure substance or impure substance. Pure substances are elements and compounds, and elements such as like hydrogen, carbon, iron, compounds, water, and ammonia, and those things that are fixed. And elements, you can have metals, nonmetals, metalloids, and noble gases. For impure substances, you can either have a homogeneous mixture or a heterogeneous mixture. Be sure to be able to classify if they give you an example. So pure substances, element, it's made up of only one element. A compound is made up of two or more elements. For mixtures, we have homogeneous if it's uniform throughout, and heterogeneous if it's not uniform throughout. So for homogeneous, you can have apple juice. For heterogeneous, you can have chicken noodle soup. And then for compound, you can have sugar. So just some examples. Properties. So a physical change is done without changing composition. So most of these are like changing of state of matter, because the element or the compound is still the same. You haven't changed any of its properties, whereas a chemical change is change. Like the chemical composition of the thing is changed, like burning or bleaching. So classify each of the following as physical or chemical change. A copper wire is hammered flat. Even though like it's squished, it's still a copper wire. Like it's still the same. So it's physical. A nickel dissolves in acid to form a blue-green solution. That's chemical because you already changed the properties of it. Dry ice sublimes without melting. That's physical. A match ignites when struck on a flint. That's chemical. All right. So we get into like conversions. The question says 3 samples, each of a different substance, are weighed and their volume is measured. The results are tabulated below. List the substances in order of decreasing density. So they give you mass and volume, but they're all in like different units. So what I do is change all of them to the same unit so I can compare them. So I change all of these to grams, and I change all of these to liters. So for 1, and density, remember, is mass over volume. So for 1, it's 10 grams over 0.01 liters. So that's 1,000 grams over liters. 2 is and then 3 is 0.012 over this huge number. All right, so we see there, be careful with like what the question says. So it's decreasing density from highest to lowest. Don't get those confused because, yeah, those are easy points. So the biggest one is 3, followed by 1, followed by 2. So that's C. All right, measurement, accuracy versus precision. They like this concept a lot. It's something that like you'll see even in like higher chemistry classes. Accuracy is how close to the actual value a measurement gets, and precision is how close the repeated measurements are to each other. So if you were to recognize a diagram, you could see it as accuracy. So keep in mind that like you want to hit like the middle. So this would be something that could be accurate. This could be something that could be precise because it's the measurements are close to each other but are not close to the target. And then you could have both where like all your measurements are accurate and precise. Accurate and precise. All right, you're good? So, like I said, they like diagrams a lot and like, so be able to recognize stuff. There's also a graph method if you prefer that. So the first one would be inaccurate and imprecise because he didn't get close to the target value or none of the measurements were close to each other. Inaccurate and precise because even though he didn't get it, all of them are close to each other. And then accurate and precise, which is what we aim for when we do experiments. Significant figures, even though this seems like simple, don't forget about it. It can make a difference in a question. Calculations in multiplication or division, you choose the lowest number of significant figures, whereas addition, subtraction, you use the lowest number of significant decimals. So if you calculate this, so this is multiplication and division, so this first one has 5 sig figs. This one has 3, because the zeros don't count. 3 sig figs. And then this one has 1, 2, 4. So our final answer should have 3 sig figs. And when I calculated that, I got 0.121, which is A. All right. Atomic laws. So law of conservation of mass. Mass is neither created nor destroyed. Law of definite proportions. All samples of a compound have the same proportion of their constituent elements regardless of where the samples were taken. So if you take like 2 samples of sugar, the composition of like C2H2O is going to be the same as like from another one for a bigger amount. Law of multiple proportions. When 2 elements form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So just keep those in mind. Discoveries. J.J. Thomson discovered the electron with cathode rays and deduced electrons are negatively charged. Robert Millikan measured the charge of the electron, and Rutherford developed the nuclear theory, which states an atom is mostly empty space with most of its mass concentrated in the nucleus. So I remember a question I had. I don't know if it was the ACS, but it was for sure in one of my tests. Was what did Rutherford's experiment prove? It proved atoms are mostly empty space. So before they used to think it was like that and the electrons were plugged. And then we went to like what we know today, where like they're mostly empty space. Okay, atomic theory. I keep in mind I put like the page numbers on for the textbook in case you want to check back on some things. The atomic theory states that each element is composed of atoms. All atoms of a given element have the same properties that distinguish them from other elements. Atoms combine in single whole number ratios to form compounds, and atoms of one element cannot change into atoms of different elements. So who proposed it? Proposed atomic theory. Dalton. All right. So now we get into like composition of elements and how to recognize those things. So we usually see elements written like this, where A is the mass number, Z is the atomic number. And so remember, the atomic number we can get from like the number of the element, and that determines number of protons. And mass number is determined by protons plus neutrons. I don't know if you can read that. Okay. All right. And this is like the chemical symbol. All right. Isotypes. Oh, it's isotopes. Sorry for that typo. Isotopes, it's a change in number of neutrons, whereas ions are a change in number of electrons. So if they give you like a question where they're showing you different elements with different like mass numbers, and it's the same element just with different mass numbers, then what's changing there is the neutrons. So, and it's going to be a question about isotopes, so keep that in mind. So ions, when they change their number of electrons, they form either positive ions, which are called cations, or negative ions, which are called anions. So a way to remember it, cations, cats are good, so that's positive. Anions sounds like onions, so that's bad, so they're negative. I don't know. Mnemonics get you through college. Okay. All right. Determine the number of protons and neutrons in the isotype. Why do I keep saying isotype? Isotope. Isotope. Fe58. So this 58 is the mass number. So mass is 58. So remember, that's protons plus neutrons. And then iron's atomic number is 26 protons. So iron's atomic number is 26, which tells us that there's 26 protons. So if we want to get how many neutrons, we subtract the mass number minus 26, and that gives us 32 neutrons. So right away, you can cross out anything that has 58 for number of neutrons, because you know, like, that's not the case. And then our answer is C. All right, so going into isotopes. A naturally occurring sample of an element contains only 2 isotopes. The first isotope has a mass of 68.9 and some change, and a natural abundance of 60.11%, and the second isotope has a mass of 70.9. Find the atomic mass of the element. So remember that since there's 2, well, like depending on how many isotypes you have, they still have to add up to 100%. And the way you solve this is, we're looking for the atomic mass of the element. Remember that with isotopes, our total mass of the element is going to be a combination of the isotopes and their abundances. So for the first element, 5, 5. And then 70.9247. So what I did, you have to like multiply the weight times the percentage, like the natural abundance divided by 100 plus the other one, same thing. So since the first one had a natural abundance of 60.11, then the other one must have 39.89% abundance. And so calculated that, 43,112 plus. And that gives us, and so if they ask you what element is this is gallium, because this is its like actual mass number or weight. Element number 31. So that's B. So keep in mind that the actual weight of the element is going to be closer to the isotope with the highest abundance. So it's closer to 68 because the one that's 68%, the one that's 68.9 is 60% abundance, whereas the other one is only 39%, if that makes sense. Can I flip it? Yeah? Yeah? Okay. All right. Determine the number of atoms in 1.85 milliliters of mercury. The density of mercury is 13.5. Let's flip this. Okay. So we have 1.85 milliliters times 13.5 grams over 1 milliliter. Remember, we can use density as a conversion factor. And we want to cancel milliliters, and we want grams, so we get 24,975 grams. And so we can use that to change it into moles. So the weight of mercury is 205.92 grams. So we cancel out grams, and we're left with moles, but the question is asking us for number of atoms. And we know that in 1 mole, there's 6.022 times 10 to the 23 atoms. It's here. And then the answer is 7.50 times 10 to the 22 atoms. So C. Okay. By the way, most of these like multiple choice questions are from the end of chapter quizzes on your textbook. So I found those really helpful. If you, like, especially for the final, if you're having trouble with the chapter, do the end of chapter assessment and see how you do and what to focus on. So type of chemical bonds. So ionic, remember, is metal, non-metal. Should be a plus sign actually. So metal plus non-metal. Covalent is non-metal plus non-metal. And metallic are metals. All right. So I left this space because I wanted to write like a chart comparing metals and non-metals, and then ionic versus covalent. I'll cover ionic versus covalent in a moment. So metals, most are solid. at room temperature, except mercury, shiny, good conductors, ductile, and lose electrons easily to form cations. Remember that the electrons they lose are the valence ones, like all compounds, all elements. Nonmetals are brittle, are poor conductors, not shiny, and easily gain electrons. Share or gain electrons and anions. So remember, metals are on the left side, nonmetals are on the right side of the table. So ionic versus covalent. So this chart is related to the type of bond. So ionic bonds involve transfer of electrons. Remember, ionic, so it starts with I. I don't like to share, if that helps you remember. So it's transfer of electrons instead of sharing. High polarity, high melting, and boiling points. And then they're metal plus non-metal. Covalent, sharing, low polarity, usually, low melting points and boiling points, and they're non-metal plus non-metal. Skipped an N there. Oh, sorry. Okay. Can I flip it? No? Okay. Ready? Yes. Yeah? Okay. Okay. Common polyatomic ions. By now, you should have these memorized. If you don't, you gotta cram for them. All right. This is from your textbook. Keep in mind one key. This is the only thing I have to tell you guys how to help you remember. But depending on the number of oxygens, then the ending changes. So nitride only has 2 oxygens, nitrate has 3, and so on. I also when I was learning them, I also classified them by their charge. So the ones that have -1 charge, the ones that have -2 charge, the ones that have -3 charges. That helped me, just because of grouping. Yeah, that's all I can tell you. All right. As far as, you can barely see this. Okay. As far as naming goes, this chart is your best friend. Is 3.10 on page 105. Because it summarizes all the compounds you can have and how to name them. So I'll go through them real quickly. So ionic compounds we already said is metal and non-metal. If the metal forms one type of ion only, then it's just cation plus the anion, and the ending of the anion is IDE, like sodium chloride. If the metal forms more than one type of ion, that's when you use the Roman numerals in the middle to classify that. For example, iron chloride. I don't know why that. Okay, because it has to be. So let me write it, because I don't think you guys can see it. Chloride. That's a 3 inside of the parentheses. Sorry. All right. Molecular, non-metals only. So remember, we use, when we are naming molecular compounds, we use prefixes. So prefix, name of first element, prefix, base of name of the second element. If the first element is only 1, you don't use anything because it will be mono, and we don't use mono at the beginning if it's like the first one. So diphosphorus pentoxide, because we have 2 P's and 4 O's. And then acids, we have, if it's binary, so with no oxygen, we have hydro, base name of the nonmetal plus IC, and then acid at the end, like hydrochloric acid. For oxy acid, so compounds containing oxygen. If the polyatomic ion ends in 8, then you change it to ic. So phosphoric acid, if it ends in ITE, then it changes to OUS acid. So it's just a little practice. All right, so let's do some practice. All right, so BaNO3, 2, barium nitrate. There we go. Copper chloride, so CuCl2. This one is dichloride monoxide. This is tin. That'll be 2 oxide. Manganese oxide, so MnO2. PCl5, pentachlorous, pentaphosphorus, no. I read the 5 first, sorry. Phosphorus pentachloride. And then chromium nitrite. Okay, good? Yeah. Where? This one? Oh, sorry. Which one? Dichloride monoxide, yeah. Because it's covalent, right? So we have 2 chlorides and 1 oxygen, so dichlor. Yeah, that's what I have. Oh, DE? Yeah, that's what I have. Still double check me. All right. Okay. So we get into like more calculations. So percent composition. Remember, we can find the percent composition of an element in a compound. So in order to do that, mass of element in 1 mole of compound divided by mass of 1 mole of compound times 100. And so I'll show you what that means. So yeah.
The dichloride monoxide is supposed to be dichlorine.
Oh, okay. Thank you. There we go. Yeah, guys, double check me. All right. Thank you. All right. Okay. So list the elements in the compound in order of decreasing mass composition. So this is our element. So in order to do that, we find the weight of the element. We have 2 in there. 70.9 grams per mole. For fluorine is 19 times 2, 38 grams over mole. And then carbon, 12 times 1, So the times is how many we have in the actual compound. We get 12 grams per mole. And then our total is 120 grams over mole. So now to find the percent composition of each in the compound, we just divide that by that times 100. So all of these divided by 120.9 grams over mole. So C is 58.64. F is 31.43%, and then CL is 9.93%. So that's A. Because carbon is the highest, and then fluorine, and then chlorine. Okay. Alrighty. So we get into percent yield. Percent yield, remember, is actual yield. Oh, it's missing the slash. So divided by theoretical yield times 100. So actual is the one like actually worked in an experiment. Theoretical is the one you should get times 100. It's never, so it's equal or less than 100%. Theoretical yield, calculate our amount of product based on a chemical equation. Actual yield, actual amount of product produced when doing our reaction. So limiting reagent, the reactant that limits the product. So all of it is used when, like, in these type of problems, it's always used completely. Etz's reagent is the reactant that doesn't limit the product. So in these type of like word problems, you'll have like some left. Okay. Remember, molarity is moles over liters and tells us concentration of something. Yeah.
That previous question, I think it should be switched. I think CL is the biggest one. Because if you do 12, 5,
Oh, really?
it's 9. Yeah.
Okay. Well, okay, so it should be C? Okay. D? Okay. So 58.64 is for chlorine? Okay. Okay, there we go. Thank you, guys. All right. You see, be careful with that. All right. Yeah.
Is there a difference between limiting reagent and limiting reagent? Is there a difference in those words? Or does it not matter?
I don't think so. It's usually as like reagent
It's usually reagent.
or reactant. But
Yeah, reactant reagent.
oh no, I don't think so. No.
They're all the same.
Yeah. All right.
And then there was one where they're opposites, like limiting agent is like the one that makes. Oh, I'm thinking reactant.
I don't know about that.
Redox. Sorry.
We'll get into that. Okay, molarity is moles over liters. Tells us like concentration of something. Dilution is M1V1 equals M2V2. Formulas. Empirical is the lowest possible number of subscript. Molecular is actual number of atoms in molecule. And structural, the lines represent which atoms are bonded to each other. So there's a relationship between molecular formula and empirical formula. Molecular formula is equal to empirical times N. So we'll get into an example. All right. So the empirical formula of butadiene, probably not saying that right, is C2H3O, and its molar mass is 86.09 grams over mole. Find its molecular formula. So we take the compound and we see how much it weighs. So 12 times 2 equals 24. H equals 1. Well, yeah. So that's 3. And O equals 1 times 16 equals 16. So our compound weighs 43 grams over mole. So this is the weight of the empirical formula. Was that me? Sorry. Empirical formula. And so now we have to find its molecular formula. And we can do that by using this. So molecular mass divided by empirical mass. It's going to give us N value, like how they're related. So they told us it was 86, so 86.09 grams or mole for the molecular one, and 43, which we just calculated, grams over mole, is equal to 2. Well, it's equal to N, and then so N is equal to 2. And so we take our empirical formula. Let me zoom out a little. C2H3O, and multiply all the subscripts by 2. And so we get C4H6O2. That's our molecular formula. Good? Yeah? Okay. Upon combustion, a sample of 30.42 grams composed of only carbon, hydrogen, and oxygen produced 35.21 grams of carbon dioxide and 14.42 of water. What is the empirical formula of the compound? So for this, you're like working backwards because they are telling you what you started with and then what you produce, but they don't tell you how many. So we take 35.21 grams of CO2 and convert it to moles. And we know that in 1 mole of CO2, we have 1 mole of carbon. So that gives us 0.8 moles of carbon. And we want to convert it to grams to like be able to find all the components. So carbon weighs 12 grams. And that gives us 9.6 grams of carbon. We have to do the same thing with hydrogen. So 14.42 grams of H2O. There's 18 grams in 1 mole. And then in 1 mole of H2O, there's 2 moles of hydrogen. And that equals 1.6 mole of hydrogen, which equals 1.6 gram of hydrogen. Okay. And then for oxygen, the way to find oxygen is by having the initial value minus the addition of the contribution by carbon and hydrogen, and we get 19.22 grams of oxygen. The reason we have to do this is because oxygen is present in both compounds. So you can't use the same method to find oxygen, so you have to do it this way. And convert it. Gives us 1.2 moles of oxygen. All right. So now in order to find the empirical formula, we have to divide everything by the lowest one. You remember that? So the lowest one is, where is it? So the lowest moles. So the lowest one is carbon. And then H, we have 1.6 moles divided by 0.8 moles. And then oxygen is 1.2 divided by 0.8 moles. So when we do that, we get C is 1, H is 2, but O is 1.5. And remember, we need whole numbers, so we have to multiply by 2 to get this to be a 3. So C2H4O3. So that's our initial compound. Yeah? Well, that's the empirical formula of the initial compound we use. Can I flip it? Yeah? Okay. No, let me see. I think I pasted this for the sake of time, but I might have to rewrite it. I don't know if you guys can read it. I think you can. Okay. So if we have 4.95 grams of ethylene, so this goes into like limiting reagent and Etz's reagent and all that. So if we have 4.95 grams of ethylene and are combusted with 3.25 grams of oxygen, so remember, so they're asking what is the limiting reagent, how many grams of CO2 are formed, how much Etz's reactant remains after the reaction. So remember that even though they didn't give you a formula, you can write it out. They give you ethylene, so C2H4 plus oxygen, because the combustion happens with oxygen, and they give you that. And then the products are carbon dioxide and water for all combustions, and then you can balance it. I don't know if your questions will be that complicated, but you can find it if they don't give it to you. So what is the limiting reagent? So you have to compare how much of each, so how much would each produce in terms of like one product, and you have to compare the same product for both. So 495 of ethylene converted to moles. So we convert it to moles and then compare it to see how much we get of carbon dioxide. So 1 mole of C2H4, based on the equation, is equivalent to 2 moles of carbon dioxide, and we convert that to grams. So that gives us 15.5 carbon dioxide, 15.5 grams. And if we do the same with oxygen, the same process, we change it to moles, and there's the equivalence is 3 moles of oxygen to 2 moles of carbon dioxide based on the formula again. And carbon dioxide is 44 grams, so you change that to grams. You get 2.98 grams of CO2. Of course, O2 is limiting, if that makes sense. And then how many grams of carbon dioxide are formed? You only form 2.98 because since oxygen is limiting it, you can't form beyond that. It's like, all right, how much of the Etz's reagent is left after the reaction? So based on how much you form, that's how you find out how much is left. So 2.98 grams of carbon dioxide, you compare it again to the Etz's reagent. So 2 moles of carbon dioxide to 1 mole of C2H4. You change that to grams. So you consume 0.950 grams of C2H4, which is essentially nothing. And you subtract it from the initial amount. So 4.95 minus 0.950, and you have left 4 grams of C2H4. There's many ways to find this one, but I usually use this method, like going backwards. And they tell you if the reaction achieved a 61.5% yield, how much CO2 that you produce. So you find your CO2 produced. But it's usually, for this, it's usually these two. And then the third one would be like actual calculate percent yield. It's usually not like this. All right. So balancing. If you're in a time crunch, you can always like plug in this to that, but that might take longer. It's just like, I don't like advise it, it's just like last minute resource type of thing. But in order to balance it, I usually do like a little chart. So on the reactant side, how many P's we have, how many Cl's we have, how many H we have, how many O's we have. Same for this side. So P, let me do it in pencil. P, we have 1 here, 3 here, 2 here, 1 here. Then for this side, we have 1 P, 1 Cl, 3 H's, and 3 O's. So clearly it's not balanced. So start balancing it. I would start with this. So 3 Cl's, HCl, to change this. And then that also changes this to 6. And so now you have 6 hydrogens on this side, but only 2 on this side. So you do the same. So 6 hydrogens now, 3 oxygens, and so our equation is completely balanced on both sides. So that might take time. It's just practice. So the more you do, the faster you'll get at these. So our answer for this is A. And for this one, you do the same. You get 2 here, 3, and then 4 and 3 for it to be balanced. Okay. So solutions. The solvent is a component with the highest volume. It's usually water. Solute is the component other than solvent. Solution is solute plus solvent. So remember like the types of electrolytes we can have. So electrolytes can be strong, weak, or non-electrolytes. Strong dissociate 100%. So when you're thinking of these, think of strong acids, strong bases. They dissolve completely. Weak electrolytes only dissociate slightly, less or equal to 5%. So think weak bases, weak acids. Non-electrolytes do not ionize in water, so like covalent bonds. Sugars don't form ions in solution. Solubility rules. I know that if you're in Dr. Patino's class, you'll get this, but I would say practice some before walking into the test. Like practice with the table, with the one he gave you, to see if something is soluble or not. Because it's for time purposes. All right, let's see how much we have. We're almost done. All right. switch to this. So we can either have molecular equation, complete ionic equation, or net ionic equation. Molecular equation is one where ionic compounds are expressed as molecules instead of component ions. And then we have complete ionic equation, where electrolytes in aqueous solution are written as dissociated ions. And then the net ionic equation omits spectator ions. So remember that when we say that you omit spectator ions, we mean you omit the ions that are not involved in making the precipitate, right? So I'll give you an example. I don't have much space, but I'll try to write tiny. So let's call these 1, 2, and 3. So let's say we have silver nitrate plus sodium chloride, and that forms silver chloride and sodium nitrate. That should dissolve. All right, so that's our molecular equation. For 2, for the ionic equation, we see what dissolves and what doesn't, and we write them as ions. So we know this is soluble. So these 2 are soluble. This is soluble. I'm going to write it below. So our silver chloride is not soluble though. So that's the precipitate. But from sodium nitrate, they still dissolve. So that's our complete net ionic equation, including everything, including all the ions, including the precipitate, including everything. But for our net ionic equation, we cross out anything that's not involved in making that precipitate. So Ag and Cl stay, nitrate and sodium go. And so all right, good? Okay. Okay, acid base. Acid is a substance that produces H's or protons. A base is a substance that produces OH's or hydroxides. And neutralization reactions are those in which we have an acid plus a base and we produce a salt and a water. Remember that salt is just an ionic compound. Like this, for example. All right. Titrations are used to quantify the concentration of an unknown acid or base using the opposite with a known concentration. So the question asks, calculate the molar concentration of HCl in a solution if 35 milliliters of the acid required 28.9 milliliters of a 0.178 molar solution for titration. So first thing we have to do is write the equation. Remember, since it's titration, it produces salt and water. In order to find the product for that, remember that you can cross them. So this one associates with that, and this associates with that. Like the plus with the minus, and that one with that one. All right, so we form KCl and water. And they told us that we needed 35 mils of this, which is 0.035 liters. We used 0.289 liters. Okay. So we work based on the equation. Liters of KOH times let's do. All right, so we used how many milliliters the titration required of the base, and we used the molarity as a conversion factor, and then we related back to the equation, and we found that 1 mole of hydrogen chloride is equivalent to 1 mole of potassium hydroxide, and that gives us how many? 0.05144 moles of HCl divided by the amount we use. So that's equal to 0.15 molar of HCl. So we started not knowing the molarity of HCl, and we found it. We good? Okay. All right. Redox reactions. So oxidation is losing an electron, reduction is gaining an electron. So remember the mnemonic. I have no space now. I'll write it here. So oil, rig, oxidation is losing electrons, reduction is gaining electrons. And remember that when we're talking about agents, they're flipped. I think that's what you were talking about. Yeah, okay. So the compound that gets oxidized is the reducing agent, whereas the compound that's getting reduced is the oxidizing agent. So every time you have a redox problem or a question, write this chart. Like, that's gonna help you not make mistakes. Just write it out. It takes like a second. All right, can I flip? No, okay. I still use this to this day. Yes. This is really important. All right, can I flip it? Yeah. All right, oh, I cut on the rules to assigning oxidation numbers, so make sure you know these. remember that the oxidation number of an element is different than the anion or like ion it makes. Do not mix those up. All right, so know these rules. Elements in their elemental form have an oxidation number of 0. The oxidation number of a monoatomic ion is the same as its charge. Nonmetals tend to have negative oxidation numbers, although some are positive. Oxygen has an oxidation number of -2, except in peroxides, and then it becomes -1. Hydrogen is -1 when bonded to a metal and +1 when bonded to a nonmetal. Fluorine always has an oxidation number of -1, and the sum of oxidation numbers in a compound is equivalent to its overall charge. So, yeah. So let's look at nitrate. So it's a -1 charge. So we don't know the oxidation number of nitrogen. We can't assume. We don't know that. The only one that's set is the one for oxygen, so, and we know that's -2 times 3 because there's 3. And then these two have to add to -1 because that's the charge of the whole compound. So, not just the oxygen, the whole thing. Does that make sense? So, when you solve this out, we find that nitrogen is +5. Its oxidation number. So, same thing with carbon in this compound. So CO3, -2. We don't know it for carbon. And carbon has like a wide range of oxidation numbers. So Et plus, same thing, -2 because oxygen is -2 times 3. But this time, everything has to equal to -2. Keep in mind that your test may now have it in parentheses, like the compound, so you have to know that that charge outside, like above, is for the whole compound, not just for oxygen or like the element that's there. So when you solve this out, you find that carbon is +4. So that's 8. So if you forget all the rules, hopefully not, remember that oxygen is -2. Yes. Oh, that wasn't a question? Okay. All right. Determining whether the following reaction is a redox reaction. If it is, identify the oxidizing agent and the reducing agent. So let's do that. So this is an element by itself, so it has an oxidation number of 0. Same for O2 in this case, but in this case they're combined. So let's see. So oxygen in this case, of course, is -2. So magnesium has to be +2, right? So now let's analyze which one. I mean, it is a redox reaction because their oxidation numbers change. So magnesium went from 0 to +2. So it lost electrons. So that's oxidation. Oxidized. Whereas oxygen went from 0 to -2, so it gained 2 electrons. It became more negative, so it got reduced. And so now I write on the side, this is how I solve them, and it helps you not make mistakes. So the one oxidized was magnesium, the one reduced was oxygen, and so oxidizing agent is oxygen and reducing agent is magnesium. You flip them. All right, good? All right, so we get into thermochemistry, everyone's favorite chapter. All right, these are some equations that you should know. by memory. Especially these. I should stop doing that because I'm gonna like point at all of them probably. But like, know those equations. Sorry. All right. In an exothermic reaction, energy is released into the surroundings as heat. As a result, the temperature of the surroundings increases. In an endothermic reaction, energy is absorbed from the surroundings. As a result, the temperature of the surroundings drops. So if you think about it, exothermic is negative, and then endothermic is positive. So endo, if you put stuff into it, it's positive. So think about like your bank account. You always want to put money into it, not take out. So it's positive since you're putting in heat or energy or whatever. Yeah, okay. So for calorimetry, we have coffee cup or bomb. So coffee cup measures the heat of a reaction at a constant pressure. The equation is Q of the solution equals M of the solution times CS times change in temperature, and we call that like you need coffee for the MCAT. So that's your mnemonic for that one. And then bomb measures internal energy of a reaction at a constant volume. And so we have Q of calorimeter equals C times change in delta. So you need coffee for the MCAT, so MCAT, versus CATs are the bomb, so CAT for bomb. I didn't go in depth about like these two, but if you visit my website, exam 3 is there, and it has the solutions, and it has problems on both bomb calorimeter and coffee cup. You might have to like scroll down a bit though. All right. A chemical system produces 155 kilojoules of heat and thus 22 kilojoules of work. What is the internal energy of the surroundings? Oh, I didn't go into like the chart. Okay, make sure you know this chart. So Q, W, and E. So if it's positive, it's endothermic. Thermic. If it's negative, it's exothermic. Work is positive if work is done on the system. On system. But it's negative if the system has to do work. So work done by the system. So think about it. If you're lazy, you don't want to do work, so that's negative, right? And then delta E, energy into, energy out of. So this is table 6.3, page 254. It's on your chapter 6. All right, so a chemical system produces 155 kilojoules and does 22 kilojoules of work. So it produces negative, does 22, that's negative 2 because it's doing it. So remember our equation, Q plus W. We get negative 177. Now be careful because what we just calculated was for the system, but they're asking us for the surroundings. Remember that they're flipped. So the energy of the surroundings is so energy of the system is equal to the opposite of the energy of the surroundings. So this means that negative 177 is actually positive for the surroundings. So that's A. So be careful about which one they're asking you for. All right. How much heat must be absorbed by a sample of 15 grams of water to raise its temperature from 25 Celsius to 55 Celsius? And they give you the specific heat capacity of water. So remember our formula. 15 grams, 4.18 joules. And then remember, change in temperature is final minus initial. Remember that in this formula we use it in grams, like the mass is in grams and the temperature is in Celsius. If you're ever unsure, look at the units for the specific heat capacity, so they cancel out. So that's B. All right, can I flip? Yeah, okay. We're kind of running out of time, so. But you can take pictures at the end if you want. All right. So Hess's law, remember we saw it twice, like in chapter 6, and then we saw it recently again. So if a chemical equation multiplied by some factor, then the delta H is also multiplied by that factor. If chemical equation is reversed, then delta H changes sign. If chemical equation can be expressed as the sum of series of steps, the overall reaction is the sum of delta H for each step. So this is from like the exam 3 with the solutions that's on my website, not the Studio Union one, like my WordPress one. So they give you one. So you want to determine it for this one, and you have to determine it from both. So for PCl5, I don't know if you can see, we need 4 of these on the product side. So we flip it. We multiply it by times -4 to have 4 of that, just as in like the initial equation, and then flip it. And then we cross out what we have on both sides and end up with the initial equation and then how much energy it took to produce it. Okay. And then we also have standard enthalpies of formation. So this is to be used with Lewis structure. So delta H of the reaction is the sigma of the moles of the products and their energies minus the moles of the reactants. Like how much it takes. It's also on that exam 3. So this is where you look at what bonds were broken and what bonds were formed. So if you have questions on that, take a look at that. So we get into energy. Make sure you know these two, and then the constants are given, so don't worry about that. So energy is equal to Planck's constant times the frequency. Frequency is equal to the speed of light over the wavelength. So and then the Broyle's wavelength is equal to Planck's constants over mass times volume. No, mass times velocity, sorry. Not volume. All right. So electromagnetic radiation, have a general idea of where each of these things are set. So know that the radio waves is on, like, has a really long wavelength and a short frequency, whereas like gamma rays are on the opposite side, and like where's visible light fall on that area, on that like diagram. The speed of light, so that's c. And then frequency is the number of waves that pass a point during a certain period of time, the greater the wavelength, the smaller the frequency. So then higher frequency equals higher energy. And so that means that frequency and wavelength are inversely proportional. Same with energy. So energy and frequency are inversely proportional to wavelength. So let me make brackets. So energy, wavelength. But if you're talking about energy and frequency, then they're directly proportional. Like here, higher frequency equals higher energy. Okay, so we get into quantum numbers. So, of course, we have, so what are our four quantum numbers? Remember, we have N, we have L, we have ML, and we have MS. So energy level, shape of orbital, which we find n minus 1, remember? Like that's the maximum. ML is based on L, so from negative n to positive n value. And then MS is the spin of the electron, either plus 1/2 or minus 1/2. So no two electrons can have the same four quantum numbers. Remember, that's the Pauli exclusion principle. No two electrons have same. Oh, yeah, sorry. There you go. No two electrons have same quantum numbers. I don't know why I wrote that way. Sorry. Okay. So, yeah. Good. Yeah? Okay. All right. Which of the following represent valid sets of quantum number? For a set that is invalid, explain briefly why it's invalid. So, n equals 3, L equals 2, ML equals -3. So this is not valid because ML had to be a maximum of +2 or -2, but it's -3. So N2, L1, M equals +1, that's valid. C, N equals 6, L equals 5, ML equals -3, that's valid because all of them are within the range they're supposed to be. And then D, N equals 4, L equals 4, ML equals +3, that's not valid because L has a max value of 3. All right, so this is just to show you how many orbitals we have and how many electrons we can fit in, because, yeah.
For C, wouldn't it be not valid because of the same reason? Because L can be
For this one?
yeah.
But N equals 6 though. So 1 less than that is 5 for L. So there is. We just don't cover everything. All right. So we have 1s orbital, which means we can have 2 electrons in there. We have 3 p orbitals, which means we can have 6 electrons in there. There's 5 d orbitals, which means we can have 10 electrons when we're doing our electron configuration. Then there's 7 f orbitals, 14 electrons. Remember that for your L values, the ones we use, if it's 0, then that's S. If it's P, if it's 1, then that's P. If it's 2, then that's D. And if it's 3, then that's F. Alrighty. Okay. Orbital filling. Electrons occupy the lowest energy orbital available, so you have to fill in 1s before 2s. Fill in the following order. So I tend to use the periodic table one instead of like the electron, the upside down rain method, but it's up to you guys. Keep in mind of the rules. So Pauli exclusion principle, no 2 electrons in an atom can have the same 4 quantum numbers. Hund's rule, when filling degenerate orbitals, electrons filled them singly first with parallel spins, and then off-ball, lower energy levels are filled first. So a representation of Hund's, so imagine we have our p orbitals, so we have 3. You fill them first individually like that, and then you pair them. And remember, orbitals can only hold 2 electrons each. All right, can I flip? No. Okay. All right, so writing electron configuration, writing all of the energy levels that are filled with electrons and how many in each. There's a longhand and a shorthand. The shorthand uses the nearest noble gas preceding the element in question to shorten the electron configuration. So for lithium, let me find the... So for lithium, which is here, so its atomic number is 3. So its shorthand would be the preceding noble gas, which is helium. So helium, in brackets, 2s1, because it's on the first group of the periodic table. So with the blocks, so this is S, this is D, and this is P, and then the little portion at the bottom is F. So, and you go by rows. So for example, if we were to write the electron configuration for carbon, carbon is 6. So we go 1s2, 2s2, 2p1, 2p2. So 1s2, 2s2, 2p, 2p2. Or shorthand would be helium, in brackets, 2s2, 2p2. Okay. All right, periodic trends. So make sure you understand them instead of memorizing them, because you don't want to forget them during the final. So just let's go through these and explain why that's the case for each. So let's see atomic radius first. So atomic radius increases from top to bottom, because remember, as you're going down the periodic table, you're adding energy levels. So that it increases the size of your element. So atomic radius increases that way. But it decreases that way because you're adding electrons to the same orbital, like in the same position. So it causes your atom to be reduced in size, and it's due to the C effective, or the shielding effect, which is the nuclear charge minus the core electrons. So as atomic radius decreases that way, your C effective increases. So they're inversely proportional. So for K is 19 and it has 18 core electrons, so effective charge of +1. Carbon sits on the periodic table. Core electrons is 2 equals +4. Okay, we looked at atomic radius. Let's look at electron affinity. So think about it. It increases to that side because your nonmetals really want those electrons. So it makes sense that it would increase to that side. For ionization energy is the opposite, because to take away an electron from a nonmetal is harder than to take it away from a metal. So if you can see that, then you don't have to memorize the trend, you can just understand it, because that's the goal. And then metallic character increases that way because we have the metals on this side. One thing I forgot to mention, keep in mind like how to find valence electrons for these. So valence electrons for this block is NS. For this block is NS and NP. And for this one is NS and N-1D. So those are the ones that are involved in reactions. All right. Lattice energy. Lattice energy becomes less exothermic as ionic radius increases, and it becomes more exothermic as the magnitude of ionic charge increases. So, let's see. So if we were to compare, and this is always negative. And it's for ionic compounds. So if we were to compare these two, this would have a greater lattice energy because it's a smaller distance, so those ions are being pulled together more strongly. And then for the second bullet point, if we compare NaCl and CaO, we know that this one has a greater lattice energy because of the ions they produce. So this is +1 -1, whereas this one is +2 -2. So if the charge increases, stronger hold. Okay. Lewis structures. Count the valence electrons, determine the central atom, which is usually the one that needs more bonds or more electrons. Distribute bonds between atoms and then add lone pairs to terminal atoms. And if there are any remaining electrons after terminal atoms have their octet, go to the central atom. Remember that some can have incomplete octets or expanded octets. So let me see. Okay, we're almost done. Okay. All right, so let's work on this one. So if we have, so we look at their valence electrons, we know that sulfur has 6 electrons, and that fluorine has 7 valence electrons, and there's 6 of them. So that equals to 48 electrons. Keep in mind that this is a neutral molecule. If it were like, if it had a charge, if it had like a plus, then you would subtract electrons. If it had a negative sign, you would add electrons to it, to our count. If that makes sense. So you have 48. So sulfur goes in the middle. And then we distribute those fluorines. 3, how did I draw it? One, 2, 3, 4, 5, 6. So according to the rules then, so we added those bonds, so we have to subtract them from our electron count. 2, 4, 6, 8, 10, 12. So minus 12. We have 36 electrons left. And so we fill the octets of the outside once, 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. All right, and that ends up being 36. So there's no left over for the central one. But if there were, then you would add them to the central atom. If we were to look at hybridization, so we just count the number of bonds, like how many bonds, and we go up. So let's start here, S, P1, P2, P3, because we only have 3 p orbitals, and then we start with the Ds, D1, D2. So our hybridization would be S, P3, D2. Yeah? Okay. And then if you look at the table, you'll be given, if you're in Dr. Patina's class, you see that it's 6 electron groups and that it's nonpolar. Remember that all of these on the first column are nonpolar. And that it has an electronic geometry and a molecular geometry of octahedral. So okay. All right, and it's nonpolar. Okay, bond lengths, the distance between the nuclei of bonded atoms. Single bonds are longer than double bonds and longer than triple bonds and so on. So a single bond is only 1 sigma bond, double bond is a sigma bond and a pi bond. Remember, pi bonds are formed by side-on interactions. And a triple bond is 1 sigma and 2 pi. Yeah.
Electronic geometry always stays the same, right?
Yes. So if you take away atoms and you have surrounding electron groups, so everyone here has the same electronic geometry, but not the same molecular geometry. So this one, so for this, the electronic geometry and molecular geometry would be the same. But then for these two, their molecular geometries would be different. That makes sense. So your molecular geometry changes, but your electronic geometry doesn't. Thank you. Yeah? All right. Oh. All right. Okay. The shorter the length, the stronger the bond because they're closer together. So a triple bond would hold those atoms like closer to each other. So it would be harder to break. Polarity means that one atom has a stronger pull on the electrons than another atom. Differences in electronic activities determine polarity. Nonpolar is from 0 to 0.4. Polar is from 0.5 to 1.9. And ionic is like, let's change that to over 1.9. Forgot what I was going to say. Okay. Yeah, that's the one we've been using in class. Yeah. All right. So remember the rules for a compound to be polar or nonpolar. So just take a look at those and compare and like draw some compounds and see their polarity, if they're polar or nonpolar. They like to ask about those things because they're testing on Lewis structures and polarity and how you draw them. So they're testing several concepts at once. So hybridization, count up sigma bonds and lone electron pairs determine the principal energy levels of atoms of valence electrons. Take s orbital to hybridize. Take as many p orbitals and d orbitals if applicable. Need it for same number of orbitals hybridized as sigma bonds and lone pairs. So that's what we did counting up. So just know how many you have. Oh, this one doesn't have it. Yeah. So SP, SP2, SP3, SP3D, SP3D2. All right. So state the hybridization and shape for each of the non-hydrogen atoms in the following molecule. Also state the number of sigma and pi bonds. So this is not like easier than it looks. So you count sigma bonds, so remember single bonds plus 1 of each double bond, and that's 24 sigma and 4 pi. So 1, 2, 3, 4. And then for hybridization, you do the same thing we've been doing. So for C, so you have sp2. So sp2. Remember, you only count like each bond once when you're doing hybridization. For this one, it's sp3, sp2, 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 sp3, and then be careful with the fact that they don't have lone pairs, but you know that it has to have lone pairs, right? 2, 4, 6, 8, so that would turn this oxygen into an sp3 because it has 1, 2, 3, 4 electron groups. 2, 4, 6, 8, so that would be sp1, p2, so sp2. So be careful with those things. For bond order, remember it's number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals. Be sure you can fill out, where is it? This diagram. So now we're getting into gases, which is the last one. Yeah. Will you guys get the paper on the test? I'm not sure. I would check with him before Thursday. All right, so gases. Pressure, ATM is a standard unit. 1 ATM is 760 milligrams of mercury, or 760 milligrams of 760 of torr. And a manometer measures the difference in atmospheric pressure and the pressure of the gas in the vessel. Kelvin is standard unit, and it's C, so Celsius plus 273. Density is mass over volume. And you can find mass from using PV equals nRT to find moles and then convert. Remember that standard temperature and pressure, you're going to see this a lot of times. So don't think that they're not giving you enough information. Remember that standard temperature and pressure equals to temperature of 273 kelvins and a pressure of 1 atm. Sorry. All right. We get into laws. All right. So for Avogadro's, volume of a gas is directly proportional to the amount in moles. So V1 over N1 equals V2 N2 over N2. So they're directly proportional. Boyle's volume of a gas is inversely proportional to its pressure. So P1V1 equals P2V2. So think about it this way. I don't know if you remember from when we were doing like thermochemistry. So if you have a gas in a container and then you apply pressure to it, so more pressure, less volume. So that's what Boyle's states. So they're inversely proportional. With more pressure, there's less volume because they're more constricted in there. Charles, V1 over T1 equals V2 over T2. And that says volume of a gas is directly proportional to its temperature. When you're thinking of these, like of this law, think about like hot air balloons. They fly, they're able to get lifted from the ground because you increase the temperature. So increase temperature, you increase volume. So think like that. Combined gas law, so you can get those. So P1 V1 over T1 equals P2 V2 over T2. So it's the combination of these, so you can find them. So P over T is not there. P1 V1 is Boyle's, and then V1 T1 is Charles. If you forget, no, you can find them like that. Ideal gas laws, PV equals nRT. You're going to see that a lot. Most of the calculations are done using that one. R is 0.0821 liters times ATM over mole times K. Make sure you convert PV and T to correct units. So remember that P has to be in ATM, volume has to be in liters, and temperature has to be in Kelvin. And then diffusion versus effusion. Diffusion is a collection of molecules spreading from high concentration to low concentration, kind of like the perfume he said in class. If you spray it, it's going to go away from higher concentration to lower. Whereas effusion is a collection of molecules escaping through a tiny hole in a vacuum. So like those like balloons have like microscopic air holes through where like the gas goes through. A sample of oxygen was collected by displacement of water at 25 degrees Celsius. The atmospheric pressure was 700 torr. What is the mole fraction of O2? The vapor pressure of H2O is 24 torrs at 25 degrees Celsius. So, mole fraction. So remember, it's represented by that, well, it's an ETS, like a fancy ETS. All right, so remember that the total pressure is going to be equal to the partial pressure of O plus the partial pressure of H2O. And so they told us that total pressure was 700 torr. We don't know PO, but H2O is 24 torr. So we find that partial pressure of oxygen is 676 torr. And so now that we have that, we can find the mole fraction of oxygen because its partial pressure is equal to the mole fraction of O times the pressure of, like, the total pressure. So if we do that, we're going to have PO over PT, which is equal to 676 torr divided by 700 torr equals 0.966. And it's unitless because torrs cancel out. So be sure you're able to like interconvert for those things. Yeah. All right. And what are the assumptions that are postulates of the kinetic molecular theory? So in a gas mixture, a given So in a gas mixture at a given temperature, lighter particles travel faster on average than heavier ones. So these are the assumptions. It assumes that gas particles are negligibly small. The average kinetic energy of a gas particle is proportional to temp in kelvins. And then 3, the collision, I don't know if you can read that. The collision between particles is completely elastic. So the idea of this is that these are the assumptions, but not always the collision between particles are completely elastic. Some of them are inelastic, so some particles slow down when they hit one another, and then sometimes they're not negligibly small. So there's variations to the ideal gas law because of that. Let me see what time it is. Yeah, we finished. One thing that I forgot to tell you guys, remember that for Lewis structures, if a compound has resonance structures, make sure that you're able to do those resonance structures and choose the best one based on formal charge. Remember that's a thing? Yeah. Huh? Oh, okay. All right. Good luck on your test, guys. Yeah. I think it's Thursday, right? I think it's at 4. So remember your test is at 4, not 4:30. Hi. Okay, let me.
It's on the packet.